Hello friends, in this video, let us discuss about the need for binary search trees. So we have learned about array data structures. It was simple, but was it efficient? Say this array here. If we want to search for the element 80, we have to start from the first node and then visit every element and compare the key to find it. So it will take order of n time. Same for insertion and deletion. If we need to delete 80, we need to traverse the whole array to find 80 first and then delete it. So it will take order of n time. Also, array is static. It cannot grow or shrink on demand. So that is also a problem. So it is not very efficient. For the size issue, it can be solved using a linked list. It can grow or shrink on demand. If we need to access the element 50, we have to traverse the whole linked list. So still the cost of operation is the same, order of n. So these issues can be addressed by binary search trees. In BSTs, the value of left child will be less than the value of parent and the value of parent will be less than the value of right child. So we can easily find the minimum element in BST, it will be the leftmost node. And similarly, the maximum element will be the rightmost node. In this way, for every subtree, we can easily find the minimum and maximum elements. Also, duplicate elements are not normally allowed in binary search trees. Now, let us construct a binary search tree with these elements. So first insert 100 and it becomes the root. Now as we just discussed, all the values which are greater than root will be in its right subtree and all the values which are smaller than root will be in the left subtree. Now let us insert 50. 50 is less than 100, so it will become 100's left child. Next we have 200 and since 200 is greater than 100, it will become 100's right child. Next we have 10. 10 is less than 100. So it should be placed in left subtree and we have 50 here and 10 is less than 50 also. So again 10 will be placed as 50's left child. Next we have 60. 60 is less than 100. So it should be in the left subtree and there we have 50 and 60 is greater than 50. So 60 becomes the right child of 50. Next we have 150 and 150 is greater than 100. So it should be placed in the right subtree. And in here we have 200 and 150 is less than 200. So 150 becomes the left child of 200. Next we have 300 and since 300 is greater than 100 and 200, 300 will be placed as the right child of 200. Next we have 500 and 500 is greater than 100 and greater than 200 and greater than 300. So it becomes the right child of 300. So that is how we can insert nodes to binary search tree. And see, the minimum value 10 is the leftmost node and the maximum value 500 is the rightmost node. Now let us discuss about searching and deleting a node from BST. For example, let us find the element 60. So first compare 60 with roots data. And 60 is less than 100, so we can understand that since 60 is less than 100, it can only be present in the left subtree. So we can ignore the right subtree. Now compare the key 60 with left child's data. And we got key greater than data here, that is 60 is greater than 50. So 60 can only be present in 50's right subtree. So we can ignore its left subtree and we got 60 here. Now let us find 150 and 150 is greater than 100, so we can ignore the left subtree and compare 150 with the right child 200. And 150 is less than 200, so it can only be present in the left subtree, so ignore the right subtree and compare 150 with left child's data and we got it equal, so the key is found. So like this, if we have n nodes, the total searchable size will be reduced to n by 2, then n by 4, then n by 8 and at the end it will boil down to a single element. That is n by 2 raised to 0, n by 2 raised to 1, n by 2 raised to 2, n by 2 raised to 3 up to 1. That is, in general, n by 2 raised to k, where k equal to 0, 1, 2, 3, etc. equal to 1. So n equal to 2 raised to k. Now let us take log on both sides, and we will get log 2 raised to k to base 2 equal to log n to base 2. That is, k into log 2 base 2, that is 1. So we got k equal to log n to the base 2. So if we need to search an element in a BST, so the time complexity is log n. And here we had 8 elements. So n equal to 8, which is equal to 2 raised to 3. So k equal to log 2 raised to 3 to base 2. That is 3 into log to base 2, which is 3 into 1 equal to 3. Now consider the array. We have 8 elements. So in worst case, 8 iterations are needed. And same thing happens for linked list also. 8 iterations are needed for 8 nodes. But in BST, in same case, it requires 3 iterations only. And this is why binary search tree is widely used for searching and retrieval purposes. So that's all, and in the next video, we will learn how to create and allocate memory for a single binary search tree node.